Hello everyone and welcome back to Minic Analytics. I'm very pleased to have you back once again. So in this video, we are just continuing our series, and for this case, we are going to be, the assignment for this case is that we are going to implementing regression algorithms on a given data set to predict the GPU kernel performance. So that's our objective for today. So that's what we are going to be doing today. So in the previous video, we saw how we can. So in the previous video, as I had highlighted, is that in machine learning, probably you have different types of algorithms that you can use for a specific task. But finding the right algorithm, in most cases, it's not a case of just choosing arbitrarily or just selecting by random means. You need to conduct some prior test or analysis so that you are able to select the appropriate algorithm that best suits the type of analysis that you're going to be conducting. So in the previous video, we used some algorithms and we saw how they were performing based on the different evaluation metrics that we used. And by that, we were able to rank those algorithms, starting with the one that was the best to the least. Okay, so in this case, we are just going to be using the same thing, the same processes, the same methods, the same procedures. We're just going to be applying them here. But for this case, we have changed the dataset. So instead of the housing dataset, we are using a dataset that was testing the GPU kernel performance. So that's what the dataset that we are going to be using for this case. So before we get started, if you are new to this place, please consider subscribing to our YouTube channel. We are welcoming you to our wonderful community. Hit that notification bell so that you never miss any of our updates. And if you have any questions, any query, you can leave those behind and we will get back to you. Once again, thank you for your time and let's get started. Okay, so already I have, so up to now, I think you have a brief understanding of what we are going to be doing in this case. So if this is the question that we are trying to answer, so I have stated it up here. So in this assignment, we will be implementing a regression model on a given dataset to predict the GPU kernel performance. So as usual, we are going to start by importing the libraries. So for this case, I'm going to be importing the pandas, NumPy, matplotlib, Seaborn, as well as the plotly library. I think by now you have a clue or an understanding of how these different libraries will be used. Okay, so for my case, I'm just going to execute this cell. So when we execute that, you can see that we have successfully imported these libraries onto our working environment. So after we have imported these libraries, our next step will be about importing the dataset. Okay, so we move on to that step. So all along, I'll be using comments and maybe to explain to you the different steps that I'll be taking in this analysis. So for this case, what we are doing is that we are importing the dataset. So importing the dataset. So when importing the dataset, I'm going to use the read CSV function, and I'll save my file or my data in a variable called df. Okay, so pd.read CSV. Okay, and inside the brackets, I'm going to specify the file path of our file. Okay, so my file is located here. So the file that we're going to use is this one. So what I will do is just I will copy the file path, and then I'll make sure I have quotation marks inside these brackets. Then I will just paste that file path. Then to display a portion or the first 5 rows of our data frame, I'm going to be using the head method. So I'll first say df.head. So with the head method, we are able to display our data frame. So as you can see, this is our data frame, and it shows the first 5 rows in our data frame. In this, you can see we have different types of columns. In this case, we will be calling these attributes. So these are our attributes, the columns. And inside those attributes, we have the data points. So those are our entities. So I think by now, so we have imported our data set. Okay. So moving on, I will go to the next step, which involves a data summary. So for the data summary, as I said, we are just going to get a brief description about our data. Okay, so for that, there are various ways you can do that. But for my case, I like using the info method. So df.info. So for the info method, you can see we are getting information about our data. And that information includes the range index, which displays the number of entries in each attribute in our data frame. We're also getting information about the columns. So in our case, we have a total of 18 columns in our data frame, or in our data. Also, the null count. So this displays or shows the number of values in each column. As you can see, in each attribute, we have a total of 241,640 entries or data points. So, and this number is same as for the other attributes. So in one case, we can say that we don't have missing values in any of our attributes. Another information that we do get from this is about the data types. So we can get information about the data types of the values inside the different attributes. And in our case here, we can see that we only the attributes, some attributes contain a data type integers, while others contain data types in form of the floating point number. Okay, so I think by now you have the feel of the data that we are going to be handling. Our data is pretty well organized, so we will not be venturing into a lot of data cleaning steps. Okay, so after this, the next thing that I will check, since we don't have missing values, there's one thing that we can check with our data, and that is about the duplicates. So we can check for duplicates. So checking for duplicates. So that's what we are going to be doing in this step. For this case, I'm going to be using the duplicated method. So I'll just recall my variable that contains my data, then duplicated. So duplicated. Then inside the brackets, I'm going to use an argument. So keep equals false using then outside I'm going to use the sum function. Okay, so with the duplicated method, when I specify or I pass in an argument keep equals false, this parameter means that all occurrences of the duplicated rows in the data frame will be marked to be true. Okay, and not just the first or the last occurrence of those duplicates. So every duplicate row will be marked as true. Then when we use the sum function, we are applying this so as to count the total number of true values, okay, that are in the data frame, which corresponds to the number of rows that are duplicated. Okay, so if we get a value greater than 0, that means we do have duplicated rows in our data frame. But if you get 0, it means that we don't have duplicated rows in the in our data. And if we have the duplicated rows, we will then move on to the next step, which will involve dropping those duplicates. Okay, so let's execute this cell to see if we do have duplicates in our data frame. We are getting an output of 0. So by the look of things, we can conclusively say that our data does not contain any duplicates. Okay, so the last thing about examining our data, I will be using histograms to display the distribution of data in our attributes. Okay, so we know. Okay, so basically by that we are just going to have a visual outlook of the data, and we will be using the histograms for each numeric attribute in our data. So for that, for let's say visual representation of the data. Here I'll be using histogram, so I'll say df.hist to signify that I'm using histograms. Then inside the brackets, I'll say bins equals say 50. Then for the figure size, for this one, I'm going to specify, let's use 18,15, right? Then plt.show. This is just a function to display the chart. So we can, when we execute this cell, so it's going to take some time because we have a total of 17 attributes. So when we execute the cell, this is what we are getting. So we can see the different attributes, and we can see how data is distributed in those attributes. So from the look of things, we can conclude and say that when we look at the distribution of data in the different attributes in our data, we can say that the data does not follow a normal distribution. Okay, so that means you can see that our data, we are getting several peaks, because we know data that follows a normal distribution is often in that bell curve, but here we don't. None of the columns actually has a bell curve. We can see on the run times, we can see they are tail heavy towards the right, so they are skewed. Data is skewed towards the left hand side. This step is usually useful because it will tell you if we are going to scale our data. Then moving on after this, let's move on to another step, which is all about feature engineering. So for our data, let me display the data. Okay. So when we look at our data, we can see one thing, that the last 4 columns, the run 1, run 2, run 3, and run 4, we can see that when they were testing for each GPU, they were tested 4 times. That means so for the 4 times that they were being tested, the data for the runtimes were being recorded, as you can see. So what I'm going to be doing is that I'm going to sum the data for the 4 runs for each test. Then we find the average, and that average will now become our target variable. For the feature engineering, basically we are trying to manipulate the attributes that we do have in our data frame so that we can find a better representation of the features. So for this case, it's just simple. We are adding the 4 runs for each test, for each GPU, then find the mean, and that mean will now become our target variable. So let's do that. I will start by, let's start by listing the column names for which we want to calculate the mean. So we can first list the columns. So we can list the column names for which to calculate the mean. So list the columns to calculate the mean. And these columns, so I'll just create a variable columns. Then we create a list for that. So basically, we will just copy this. So Control C. Then I'll just paste it this inside here. So that is for the column run 1. This one is for run 2, run 3, and then run 4. Okay. So by this, so I've created now the list of the columns that we're going to sum and calculate the mean. Then from here, we can then move on to calculate the mean along each column. So calculate the mean. So here, then I'll specify the target variable. So target. So that will be the new column. Then for that, say columns. Then I'll say mean, because we are performing the mean along the axis. So axis is equals to 1. Okay. Then after we have performed that, we can then display the. You can then display. The display, I'll just say again, say df.head. So when we execute this, you can see. Now, as you can see, we have created the new variable, the target variable, or the target column, which is the mean of the runtimes for each GPU. Okay. Since we have created the target column, I think these columns run 1, run 2, run 3, and run 4 now become irrelevant. So the next step after this is that we are going to drop this irrelevant column. So dropping, we will drop the columns. So when dropping the columns, we are going to use the drop function. So df.drop. Then inside the brackets, I'm going to specify, say the columns. So for the columns, that you're going to drop, I'll just copy this because they're just the same thing. So then I'll just paste them inside here. So after this, then we can to display again to see if the columns were dropped. So we can execute. Okay, so now we see that we have dropped these columns from our data frame. That we can now maybe move on to the steps which involve building our models. We can do a correlation analysis and see how our target variable is performing against these other attributes. Okay, or let's perform a correlation analysis. Okay, so say correlation analysis. With the correlation analysis, I'll be using a heat map, and for the heat map will display the values, the correlation values against the different attributes. Okay, so I'll create a variable, let's say core matrix. For the correlation matrix, df, then inside here we can pass in the different or the columns. So maybe I'll print out the columns in the data frame. So print df.columns. So here we'll just get the columns in our data frame, and I'll just copy these columns, the column names, and paste it inside
the correlation, our correlation matrix. Then we are doing a correlation, then specify the correlation. So by default, the correlation is usually the Pearson correlation. But if maybe you want to use another correlation, let's say the Spearman, you can specify, let's say, method inside the brackets. So the argument method, then you specify the correlation that you will be or you want to use. So let's say Spearman. So let's use the Spearman correlation because our data does not follow a normal distribution. And the Pearson correlation is mostly applied when your data follows a normal distribution. But since our data is not following a normal distribution, we can use the Spearman. So after we have specified the correlation, the correlation method that we will be using, as I have said, we will be using a heat map. So let's plot that heat map. So I'll start by specifying the figure size. So plt.figure. So this is the figure of our plot. Fig size equals into, let's say 2012. Then for the heat map, I'm going to be using the Seaborn library. So sns.heatmap. Then our data will be matrix, so the correlation matrix. Then I will want to annotate. So annotate true. Then I will specify the color map. For the color map, I'll be using coolworm. And for the correlation value, so I'm going to format to two decimal places, so 0.2 or two significant figures. Then specify the title of our chart. So I'll just say correlation heat map. Then plt dot tight layout. Then we display. So plt dot show. So let me just zoom in so that our figure can fit in. So when we execute this cell, we are going to get the correlation heat map. So this is the correlation heat map for our data. So you can see the different attributes. And when we look at things, or when you look at the correlation between the attributes, the correlation is closer to 0. So these attributes are less likely to be correlated with each other. Also, when we look at the target variable, so let's focus on the target variable against the other attributes. We can see there's a high 0.41 correlation between the target variable and MWG attribute, but all these others are very, very close to 0. Okay, and when the correlation is said to be close to 0, let's say 0, it generally means that the relationship between the two variables is very weak. Therefore, that a change in one variable is not well predicted by changes in the other variable based on a linear pattern. Okay, we can then move on to now start building our algorithms. So we'll start by feature selection. So we are going to select the independent as well as the dependent variables. So we are going to define the features. So when for this, I'll use the x and y. So for x, So here we can say we are going to define the dependent variables, or others can say the features. Okay, so I'll use this in a new cell. So I'll just copy this and use this a new cell. Then this one I'll convert to a text. Okay, so we are defining the dependent variable. So our dependent variable, there will be every other column except our target variable. So the easiest way to do this is to just drop the target variable from the dependent variables. So we can say df dot drop, then specify the columns, then we just specify the column, so that's the target column. And for our y, we can just now specify that our column, or the, so for the y, which is the target variable, so we can just say our target variable is the column or the attribute target. Okay, so when we execute this, we can see now we have defined the features, we have defined the dependent variable as well as the target variable. So after this, we need to move on to the next step, and the next step involves splitting. So you're going to split the data to training set and testing set. Okay, so here we will be using the train test split. So we need to import that module dot model selection import train test split. So that's the model that we will be using to perform the splitting, to split our data into the training and the testing set. Okay, so I'll execute that cell again. So here we are going to specify the training. We are going to give variables for the training set as well as the testing set. So xtrain xtest ytrain ytest. Then we recall the model, so train test split. Then inside the brackets we specify our independent features, then our target variable, then we specify the test size. So test size, in this case I'll say 0.25. so 25% of our data will be used for testing, while 75% will be used for training. Then the random state, I'll say 42. Okay, so that's how we split our data. Okay, so that cell was when I execute this cell, we'll be using the train test splits to split our data into the training set as well as the testing set. So when we are done with that, we can move on to another step. And this step involves scaling our data. So scaling the data. So when scaling our data, we want to fit our data so that they are in a similar scale. And for the scaling, I'm going to be using the standard scaler. So again, I'll start by importing the model. So from sklearn dot preprocessing import standard scaler. When I execute that cell, we will have imported the standard scaler. Then to perform the scaling process, I'll start by initializing the standard scaler. So initialize the scaler. I'll just get a variable scaler, then recall the model. So standard scaler. Okay. So after we have initialized the scaler, we can then fit and transform our extend data, so our training data. So fit and transform. So we are going to fit our scaler and transform the training data. And for the training data, that will be the attributes, so the features. I won't be scaling the target attribute. So I'll get a new variable, so xtrain scaled. So this will contain our scaled x attributes for the training data. So I'll recall them our scaler. So scaler dot fit transform the xtrain. So xtrain. Okay. So after we have fitted and transformed our training data, we are then going to be using the same scaler, but in this case we are just going to transform our testing set. So the features for the testing set. So transform the testing data. So we can say x test scaled. Okay. Then we recall again our scaler. So scaler dot transform. Then we are transforming the x test. Okay. So by this we can execute this cell. Oops, we are getting an error. So it's supposed to be scalar. Just a spelling mistake. So when we execute this, now we have scaled our data. Now the algorithms that we are going to be using here include the decision trees. So we can just say the algorithms that we are going to be using here is the decision tree. We are going to use the extra trees. So extra trees, also the random forest. Also another algorithm that we'll be using is you can also use the light GBM. Also another algorithm, we can use the cut boost. Okay, so these are the linear algorithms that we will be using in our example here. Another algorithm, I think we can work with these 5. Okay, so basically these are the algorithms that we are going to be using in this case. For the cut boost, maybe you need to import or install. For the cut boost, in most cases you will be required to install the requirements. So I'll just install that. I'll show you how you can do that. So I'll use the pip install technique. So pip install cut boost. So this is how you install. For successful installation, you'll get a message stating that installing successfully installed the cut boost. Okay,
So by this, we can then proceed. Then, so after we have done that, we can then start now building the models. So I'll start by importing the models. So importing the models for those algorithms. sklearn. So I'll start with the decision tree. So tree import decision tree. This one is not classifier. We're using the regressor. Okay, so that is the model for decision tree. For the extra trees as well as the random forest, so we are going to import from ensemble. So from sklearn.ensemble, we're going to import extra trees regressor. Okay, also from the same, we're going to import the random forest regressor. For the LGB, for the light GBM, we are going to import that. So from light GBM import LGBM regressor. Okay, then for the cut boost, so from cut boost import cut boost regressor. Okay, so we have imported. So these are the models. Also, we need to import the models for evaluation. Models for evaluation. So we will be required to evaluate and see how our models are performing. So from this, for the evaluation metrics, so from scikit-learn.metrics, import the mean absolute error. So mean absolute error. We also have the mean squared error, as well as the R2 R squared score. So those are the models that we will be using for when evaluating our models. So I'm going to execute this cell to ensure that I have successfully imported these models. Okay, so we are now moving on to building the models. So I think by now you already know how to use or how to build a model using the different types of algorithms. Okay, so for this case, remember we have 5 algorithms that we need to build the model. Then we make predictions, then evaluate the model. So if you are going to do that, if you are going to do those steps for each model, then I think we will need 4 by 5. We will need to repeat our process 20 times, and I think that is time consuming. So to avoid that, as we did in the previous video, we're just going to create a loop, and from this loop it will be iterating over and over, doing fitting our models, making the predictions, then evaluating the models. So to avoid spending more time and making our code very long, we can just use a for loop. So for us to perform that step or exercise, we need first of all to define the models. So we need to, let's say, create instance of the models.
So here we can start by say decision tree model. So for this, so we need to use a variable. So let's say for the models, we'll use a dictionary so that we can use the key and value pair. So for decision tree, we then create an instance of the decision tree regressor. So I'll just copy this, then paste it here. Then okay, so by this we are creating an instance of the decision tree. Then the next extra tree regression. So I can just say the decision tree the next will be extra trees regressor. So just copy this and paste it inside here. Then extra trees regressor. So we are creating a model for that. Okay, so we are creating an instance for that model. The next one is the random forest. So just copy that and then inside here create an instance for that. So random forest regressor. Okay, so you can using the same procedure you can create for the rest. So for the other ones, light GB as well as the cut boost. Okay, and for these two, what I've specified is the verbose to be 0. So I don't want, when this loop is running, I don't want to display the learning rate. Okay, for these two algorithms. So after we have created our loop, after we have created the instances of the models, remember we'll be printing out the output in terms of the evaluation metrics. So we need to create a dictionary that will be able to store those results. So I'll say results, then say models. So I'll again create another dictionary. So models. For our evaluation metrics, we will be using the mean absolute error. So we create an empty list for that. So mean absolute error. Then we create then for the mean squared error, MSE. So MSE. Then the R squared, let's say the root mean squared. So RMSE. Again, create an empty list for that will be storing the data. Then the R score. Again, we create another empty list that will store the data about the R squared score for each model. So after we have created this list, we are then going to move on. Maybe I can state what I'm doing here. So we are initializing a dictionary that will store our results. Okay, so here we now create a loop. So we are going to be looping over the models. So basically we are creating our loop. For our loop, so I'll be using the for loop. So for models, for model name, model in models dot items. Okay, so model name, model in models dot item. Let's see, yeah, I've used models, it's okay. So we are going to first fit the model to training data. So I will say model dot fit. We are fitting on our training data, so that is the X train. So that will be X train. So X train. Oops. So X train scaled. So then our Y train. So after we have fitted that to our training data, we are then going to make predictions on the testing data. So making predictions on testing data. So here we are going to create a new variable, ypred, and for the predictions we are going to do model.predict. So model.predict, so we are going to predict that on the X test scale. So X test scale. So basically, when we are fitting our model to the training data, we are instructing our models to learn the intricate relationship between our input features and the target variable. So that's the fitting process. So these models will learn that relationship, and after it has learned that relationship, we are going now to make predictions based on that relationship. And that's why we are passing in our X-test data. So this is a new data that our model is seeing for the first time. And after you have tested the model on the testing data, so we are going to evaluate the models. Okay, so for the models, remember we have the mean absolute error, the mean squared error, the root mean squared error, as well as the R squared score. So mean absolute error. So we recall the model mean absolute error. Okay. So mean absolute error. Then we are going to be fitting that to our Y test, as well as Y test are the actual values from our data itself, and the ypred are the data that was predicted by the algorithms. Okay, so that was for the mean absolute error. Then we move to the mean squared error, so MSE. So mean squared error, again Y test, and then ypred. Okay, then the RMSE, the root mean squared error. This is just the square root of the mean squared error. So np dot s square root, meaning to show that we'll be performing a square root for then MSE. Then the last one is the R squared score. So R squared score. Then again Y test and ypred. So after we have evaluated our models, basically we will generate some type of a result or a table. So we need to store the results in a dictionary. So we created the dictionary before, so we are going to store our results in this dictionary that we created earlier. So I'm going to say store the created results in the dictionary. So results, can say then model. So we are going to append. So for each and every model, we are going to append that. So according to the model name that we, okay. Then again for the results, we are going to this one will be for the mean absolute error. Again, we are just going to append mean absolute error. So for each model, okay. By this, we'll just be repeating this. So you can just copy this, copy. So this one was for the mean absolute error. So this one will be for the mean squared error. So M SE. Then for the root mean squared error, so you can say RMSE. Then change this RMSE. Okay. Then for the R squared score, then you can just change this to R2. So after we have stored these results in a dictionary, so this dictionary will contain individual columns as we have specified here. So we need to create a data frame for our results. Okay, so I'm going to do that. So let's say results df. So we're going to create a data frame for that. So pd dot data data frame. So we are using the data frame function, and let's say results. So we pass out this function here inside here. So after we are done with that, we are then going to display the results. So let's say display let's say output. So for our outputs, I'll just recall this variable. So results dot, I'll use the head method. So remember, we have how many models? 1, 2, 3, 4, 5. I think they will show all of them, but anyway, let's see what we'll get. So we are going to execute. So as you can see, we have shortened our work, even though it looks like complicated. But basically, what we did, we just created the instance of the models. Then we initialized a dictionary that will store our results. Then we created our loop, and this loop we called our loop. Then we fitted the model to the training data. Then we moved on to making the predictions on the testing data. Then we moved on to evaluating our models. Then from that, results that we will be getting, we stored that in the dictionary. Then we concatenated that dictionary or merged those independent columns to form a new data frame or series. Then we displayed our output. So it's going to take some time. Okay, so we just wait for a little bit to see what we will be getting. So when we execute, and after we have waited for some time, this is the output that we are getting. So as you can see, we have a table, and this table contains the models as well as the value for each evaluation metric. So we can see from the look of things, when we look at the mean absolute error, we can see that x-axis regression is the regression with the least mean absolute error at 1.37, and the R squared is 0.99. When you look at another model, the decision trees is at, you can rank it at the second with a mean absolute error of 1.489 and an R score of 0.99. So basically, you can see that most of these regressions are performing quite well. So for the light GBM regressor and the cat boost regressor, so when we look at the mean absolute error, we can see that they are quite high. So maybe when you are ranking or when you are choosing the best regression model for this analysis, maybe we won't consider those, because basing on what we are getting, they are you can say that they are performing poorly relative to the other three regression models. You can see how the different models are performing depending on the different evaluation metrics that we were using. We can also move forward and plot a scatter plot between the actual values against the predicted values. Remember, the actual values are the values that are from the data set. Those are the actual values, while the predicted values, these are the values
after applying the regression models and the scatter plots. This is just a representation of the actual values against the predicted values, and can provide insights into the performance of these models. So with the scatter plot, we are able to visually inspect or see how well the model predictions align with the actual values. So remember, we are plotting a scatter plot for all these models. So for the scatter plot, I'll start by defining the grid layout. So define the grid layout. The layouts, I'll specify the rows as well as the columns that I will require. So we have 5 algorithms. So if I use a layout of 3 by 2, I think we will be able to fit all those scatter plots. Then after this, we can then specify the figure size. So specify the figure size of the scatter plots. So again, plt.figure, then specify the figure size. So fig size. Then for this case, I'm going to be using 15, say 10. Yeah, 1510. Then again, we're just going to be looping over the models. So looping over the models. I just use the short form IDX. So for index, model name, model. So when creating this scatter plot, we can use the enumerate function. So in enumerate model.items. So again, we are going to fit the model and make on the training data as well as make predictions. So I can just copy this. So basically, we are repeating this step. So I'll just paste it here. Then after that, using our predictions, we are going to plot a scatter plot. So the scatter plots, for the scatter plots, so I'll specify the subplots. So plt.subplot, subplots, then rows, columns, and the index, so IDX. Then we plot the scatter plot, so plt.scatter. So it will be between the y-test as well as the y-pred. So our actual values against the predictions. So y-pred. Then for the alpha, this is the transparency of the points. So I'll use 0.5. Then we also require a diagonal line. So for the diagonal line, so this we'll use this code to include a diagonal line on the scatter plot, so that we can see how the points are scattering with respect to the point where the predictions as well as the actual values are equal. So the diagonal line shows where the point by which the predicted values and the true values are equal. Then we will plot the title as well as the X labels and the Y. Then we display those scatter plots. So plt.show. So we can execute this cell so that we get to see the scatter plots. So when we execute that, we can see we are getting our plots, and we can see how the different models are predicting from the results we got from the table. So we can represent this information using bar graphs and maybe compare how the different regression models are performing. So we are creating a bar graph using Plotly. So the results are from the variable results df. Then our x-axis will be the evaluation metrics. Then our y will be the models. Then I've supplied a title for our chart. Then we've customized our layout, set the figure size. Then we display our plot. We execute this cell. So we are getting an error because I think it's supposed to be models with an S. So models. So when we execute this, so this is the chart that we are getting. Okay, so I'm going to explain what we are seeing. So on the y-axis we have our models, while on the x-axis we have our evaluation metrics. So if you want to see the results or compare the results for the mean absolute error for the regression models, we remove the other evaluation metrics from display. What we are remaining with is the results for the mean absolute error. And as we saw earlier, we saw that CatBoost regressor had the highest mean absolute error, 29.11, followed by Light GBM regressor at 24.418. Extratis, as you can see, is the list. With the least mean absolute error. So if we want to see the results or display results for the R squared, so for majorly for the R squared score, we saw that most of these regression algorithms were performing quite well, and as you can see from the R squared score. So generally, in summary, so I'm going to summarize what we have deduced from this analysis. So generally, the mean absolute error as well as the root mean squared error, having lower values are what is preferred. Okay, and having the lower values again indicates smaller errors in our analysis or the data. For the R squared score, higher values that are closer to 1 are better, or we prefer those values, indicating a better fit of the model to our data. So fortunately for the results that we achieved, when we look at the scatter plot or when we look at the results that we got, we see that most of these regression models are performing quite well or are fitting well to the data. Also, when evaluating a model, it's often advisable to consider multiple metrics, as we did. So we considered different types of metrics, and by these metrics, they were able to guide us or tell us which model is performing well, depending on the data that we are using. So for the mean absolute error, the mean absolute error represents the average absolute difference between the predicted and the actual values. So basically, it measures the average magnitude of errors without considering their direction. And also for the good model, a lower mean absolute error indicates a better model. Also, a lower value signifies that a model, on average, the model predictions are closer to the actual values. So we want to be as to have lower values for the mean absolute error. For the root mean squared error, this is similar to the mean absolute error, but it gives more weights on large errors. So if we had more outliers in our data set, it could be indicated from the results of the root mean squared error, as it involves squaring the difference before averaging and taking the square root of the result. So that means it makes the root mean squared error as an evaluation metric sensitive to errors. A good model for the root mean squared means that, similar to mean squared error, a lower RMSE value indicates a better model. However, because RMSE penalizes large errors more than mean absolute error, it can be more sensitive to outliers. So maybe if you have your data has outliers, or that could have manifested from the results we got from the root mean squared error, And for the R squared represents the proportion of the variance in the dependent variable, that's the target variable, that is predictable from the independent variable. So the features, the input values that we pass into our regression models. So for the R squared, we are ranging from 0 to 1, where 1 indicates a perfect fit. Fortunately for our results, most of these algorithms were quite good in making those predictions. For a good model, a higher R value indicates a better model, indicates a better fit of the data. So a value closer to 1 means the model explains a large proportion of the variance, while a value that is closer to 0 indicates that the model does not explain much of the variance. So I think by now you have a better understanding of what we were doing. So basically this was just a test or an analysis which you can use before selecting the appropriate algorithm for whatever task you are using. So basically we are just comparing the different types of algorithms that we have, then from there selecting the best algorithm to use. I usually, for my case, I think this step is necessary because once you have selected the algorithm that best suits your case, so you are able to explain why I selected this algorithm for this data and why I dropped this algorithm for this data. So I think this step is quite important. And so I think that's all for today. Once again, thank you for your time. And if you are new to this place or if you haven't subscribed, please consider subscribing to our YouTube channel. We are welcoming you to this wonderful community. And if you have any queries, any comments, you can leave those behind. We will get back to you. Once again, thank you. And until next time, see you. Bye-bye.